Let's talk about compute. Every business needs raw compute capacity to run applications. These applications could be web servers, batch jobs, databases, HR software, machine learning, or just about whatever you can think of. The time, money, and effort it takes to get up and running with on premises computing resources are fairly high. When you own your own fleet of physical servers, you first have to do a bunch of research to see what type of servers you want to buy and how many you need to buy. Then you need to purchase that hardware upfront. You'll wait multiple weeks or months for servers to be delivered. You then take them to a data center space that you own or rent to install them, rack and stack them, and wire them all up. Then you make sure the servers are secured, powered up, and ready to be used. Only then can you begin to host your applications on top of these servers. The worst part is, once you buy these servers, you are stuck with them, whether you use them or not. It's not easy to just suddenly provision more physical compute capacity when you need it, and it's even harder to get your money back on servers you no longer need. It's impossible to get the time back. Following a compute as a service model is much easier to get started and support operations over time. AWS took care of the hard part for you already as far as getting started goes. AWS already built and secured the data centers. AWS has already bought the servers, racked them and stacked them, and they are already online, ready to be used. In a previous lesson, we showed you how to launch the employee directory application with Amazon EC2. We didn't really talk about the details, how EC2 works, what configurations exist for it, and we definitely didn't discuss any other compute options that exist on AWS. AWS has different services for different use cases, and Amazon EC2 is one of the basic AWS services that are important to understand. We'll be spending most of our time in these upcoming lessons exploring EC2. That being said, though virtual machines like EC2 are great, there are other compute services out there too, like container services and serverless compute. You'll learn about these other compute options and their use cases. Don't always assume that VMs are the default answer. Sometimes it makes sense to architect applications for serverless compute or containers from the start, depending on what you are building and what you are optimizing for. EC2 instances give you a lot of flexibility and control in the cloud, and you configure them to meet your needs. You can provision one or many instances easily, and at the end of the billing cycle, you only pay for what you use, either per second or per hour, depending on the type of the instance. When you no longer need an instance, you can terminate or stop the instance, and you will stop incurring charges. Not all servers are the same, and you are probably looking to run a specific type of operating system on your EC2 instance. AWS supports a range of operating systems, including Linux, macOS, Ubuntu, Windows, and more. To select the operating system for your server, you must choose an Amazon Machine Image or an AMI. The AMI contains information about how you want your instance to be configured, including the operating system, possible applications to be pre installed on that instance upon launch, and other configurations. You can launch one or many instances from a single AMI, which would create multiple instances that all have the same configurations. Some AMIs are provided by AWS, whereas others are provided by the community and can be found using the AWS Marketplace, or you can build your own custom AMIs as needed. For example, Amazon Linux 2 is the AMI we selected when we launched our employee directory application. This AMI is provided by AWS, and it's essentially a pre built EC2 optimized Linux image that has long term support provided by AWS. Beyond the properties determined by the AMI, you can also configure the instance type and size, which correspond to the amount of compute, memory, and network capabilities available per instance. Different applications have different hardware requirements, and choosing the instance type for your application gives you the ability to pick the hardware that it runs on. It's also really nice that you have a wide variety of choices, as it's hard to achieve that same level of variety with on premises resources. The instance types you can choose from are grouped for use cases like compute optimized, memory optimized, storage optimized instances, and more. There is a list of instance types you can find in the AWS documentation, and you can expect this page to be updated regularly as new instance types are released. For example, the G instance family are optimized for graphics intensive applications, which would work best for use cases such as 3D visualizations or video encoding. Whereas the M5 general purpose EC2 instance family provides a balance of resources and are great for applications that use these resources in equal proportions, like web servers, our employee directory application example, or code repositories. When you are launching an EC2 instance, you will see something like this when selecting an instance type and size. The T3 or A1 is the instance type that determines the blend of hardware capabilities, then the dot, then the size, like small, medium, large. It goes down to nano and up to many, many extra large sizes. The great thing about this type of selection existing right at your fingertips is that you are no longer locked into hardware decisions up front. You can choose an initial EC2 instance type, evaluate its performance for your specific use case, and then later change it to a different type that is better suited for the application. EC2 is also resizable with a few clicks in the console or can be done programmatically through an API call. All of these configurations being available to you via API enables you to embrace change over time easily as your workloads mature and change. So, okay, virtual machines are cool and totally not new. So, how exactly does this impact your business? Well, the important thing is this: the flexible and low cost nature of EC2 instances, as well as the ease of provisioning servers, allows for programmers and businesses to innovate more quickly by spinning up servers for a short amount of time to run experiments and find optimal configurations for your applications. EC2 offers a wide variety of hardware options to choose from. So you can optimize your solutions by selecting the right EC2 instance type for your application. And then you can optimize even further by right sizing the resource or selecting an instance size that is appropriate for your application and not over provisioning like is often done on premises. This type of optimization is hard to achieve on your own because with traditional on premises deployments, you are working with hardware constraints that simply don't exist in the same way with the cloud. The ability to adapt to changes and choose really specific configurations for your virtual machines all through a couple of API calls is very powerful. And EC2 is really just the beginning of the story. One of the main reasons why EC2 provides so much value is the fact that you can provision new EC2 instances on demand, and just as easily, you can get rid of instances that you no longer need. In most cases, you only get charged for instances that are currently running.
Mhm.
EC2 allows you to stop and start instances at will, which enables you to treat your fleet of EC2 instances as elastic, scaling them in or out. Then at the end of the billing cycle, you only pay for what you use. We are building up to the idea of scaling your fleet of EC2 instances in and out to serve demand. But before we get there, it's important to understand some of the more basic things about EC2. Let's talk about the EC2 instance lifecycle. An Amazon EC2 instance transitions through different states from the moment you launch it through to its termination. You launch an EC2 instance from an AMI. And as you learned in a previous lesson, once the EC2 instance is launched, it enters a pending state. This state is essentially your VM booting up. Once the instance is ready for use, it enters the running state. In the running state, you will be charged for the EC2 instance. From running, you have a couple of different options. You can reboot the instance, which is similar to rebooting, say, your laptop. It turns off, then it turns back on again. Pretty straightforward. You can also choose to stop your instance. It will enter a stopping phase, then enter the stopped phase. Stopping an instance is like powering down your laptop. You can always turn it back on, and it will go through its usual boot sequence, moving through the pending state and back to the running state. The other option, which is similar to stop, is to stop hibernate your instance. This also enters the stopping phase and then the stopped phase. You can compare this to how you lock your laptop and shut the lid, but when you open it back up, everything is still in place where you left it. No boot sequence required. You are back up and running after a couple of seconds of the computer waking up. Since the state of the machine was written to memory when you stopped it, the state of the machine can be drawn from memory and put back into place. Then you're back up and running. Now, the last option depicted here is the terminate option. When you terminate an instance, it enters the shutting down phase, then the terminated phase. Terminating an EC2 instance is like taking your laptop out for a long boat ride off the coast and throwing it into the ocean, getting rid of it forever. It's now lost in the great blue sea. There is no hope of finding your laptop on an island shipwrecked one day, having been saved after spelling SOS in the sand. Anyways, I hope you had any data or state stored on that instance backed up because once you terminate an instance, it's gone. That being said, there
Mhm.
is a feature called termination protection that you can enable if you're worried about instances being terminated accidentally. You also will learn about persistent storage and EC2 in future lessons, so don't fret. We will show you ways you can make sure your data sticks around even if the EC2 instance doesn't. So that is the EC2 instance lifecycle. It's definitely a good idea to remember how all of this works if you plan on using EC2 to host your applications. And don't think of terminating instances as a bad thing. If your EC2 instance is having technical trouble for one reason or another, maybe it needs an update or a patch, instead of logging into the instance to fix it or install software, you can launch a new one with the new changes in its place. And then you could terminate the old instance, having the new instance take that place. You, of course, can do in place updates as well, but just know that you have the option to decide how to handle these sorts of tasks. You can launch or terminate EC2 instances to meet demand. So, as demand for your application increases, you can launch more instances, and as it decreases, you can terminate instances. This keeps your EC2 instance fleet in line with demand. So, again, terminating an instance isn't a bad thing and shouldn't be feared. Now, let's discuss the cost aspect of this. You only get charged for an EC2 instance if you're in the running state or if you are in the stopping state when preparing to hibernate. This means that you can stop instances when they aren't in use. Say if you have applications that are only used during the work week, run them when your employees are clocked in, and then stop them when they aren't. Remember, you can always start from a stop state, allowing them to resume working when necessary. Hello, everyone. In this video, we are going to launch the Employee Directory application on an Amazon EC2 instance using the default VPC. So you can see I'm already in the AWS console and I'm going to navigate to the EC2 dashboard. From here, I want to launch a new instance. So I'm going to select Launch Instance and then select Launch Instance again. And now this brings us to a page where we can provide the configurations for our EC2 instance. I'm going to give this a name, Employee Directory App, and then we can scroll down and we can view what AMI we want to choose. The AMI is the Amazon Machine Image, and this is a template that contains the software configuration for your instance on boot, like the operating system, any sort of application server, or any applications that you want to have pre installed when you launch your instance. We're going to be using the Amazon Linux 2023 AMI for this, though you could browse the AWS Marketplace to get access to the different types of AMIs that vendors offer. So if you're using some sort of third party software that you want to launch on an EC2 instance, they might have an AMI out there that you could use to make your life a little bit simpler. You also can create and manage your own AMIs and share them internally within your organization to say you can only launch an EC2 instance using one of our approved AMIs that might have some specific security or compliance sort of packages pre-installed. That's another option. So leaving the Amazon Linux 2023 AMI selected, I'm going to scroll down and then we can select our instance type. The instance type will determine how much CPU, how much memory, what types of hardware is available to you on this instance. Some instances come with a GPU, for example. In this case, we're going to use the free tier eligible EC2 instance type, T2 Micro, which is the default that's selected. So we'll leave that the way it is. Then we can scroll down and select whether we want to use a key pair. The key pair is going to allow you to have access to this instance doing something like SSH. I'm going to select proceed without a key pair because if I need to connect to this instance, I'm going to use the connect button in the AWS console where I don't need to have a key pair to connect to this instance to view things like logs. Then scrolling down some more, we then can configure our network settings. This is using a default VPC and a default subnet. This default VPC is going to have subnets that have internet access. So, meaning that there is an internet gateway attached to this VPC that allows internet traffic to flow into this default VPC. You'll learn more about VPCs coming up, but just understand that this default VPC does allow public internet access, which is good for our use case, but might not be great for other use cases where you would more than likely put your instance behind something like a load balancer and then you would use private subnets. But we want to be able to access this instance directly. So, with that in mind, we're going to use the default VPC and we're also going to leave this auto assign public IP to enable. And this will allow our EC2 instance to have a publicly reachable IP address once it's been launched. Then scrolling down a little bit more, we have to configure our firewall. This is going to be our security group. Security groups are instance level firewalls. We want to disable traffic from SSH because we're not going to need that. Then we're going to allow HTTPS and allow HTTP. In our application, we're going to be using HTTP directly. Then scrolling down, we can configure some storage. We're going to leave our root volume here, but we're not going to add any more EBS volumes. Then we can expand the advanced details section, and then we need to select an IAM instance profile. In this case, I'll be selecting the employee web app role, and this role has permissions attached to it to allow whoever's using the role to make calls to S3 or to DynamoDB. We know that our application has some code that's running that's going to be making API calls to S3 and DynamoDB. We need to allow our AWS SDK to actually get access to these credentials. And the way that we do that is through this IAM instance profile. So we're associating this role with this instance profile that will allow our code to get access to these temporary credentials. Then scrolling down some more, we will come to the user data section. And this is where you can provide a bash script that will run on launch. So this script here is what's going to be used to download and install our application. Our application was written in Python using Flask as the web server. And this is going to be for our employee directory application. So on the first line, we are just declaring that this is a bash script. Then we are using wget to download a zip file from S3. So we hosted this zip file in an S3 bucket for this to be downloaded. Then we're unzipping that, and then we're changing directories into that new directory. Then we're using yum to install Python 3 and pip. Then we're using pip to install any dependencies for our Flask application, which will all be listed in a file called requirements.txt, which got downloaded from this zip file. Then we're installing a package called stress. This stress package is going to be used to simulate a CPU spike on this instance, which is going to allow us to simulate auto scaling whenever we use Amazon EC2 auto scaling in a future lesson. Then we have three different environment variables, one for our photos bucket. We're going to be using S3 to store our photos. We don't have that value yet, so we'll just leave this placeholder there. Then we have the default region. We're operating out of Oregon. And then we have our Dynamo mode on, and this means that we want our application to use DynamoDB. And then we're running this application and hosting it on port 80. Now we can select launch instance, and this will begin to go build out the different things that we need, like our security group, and we can see that our instance has launched. It means that we want to be using S3 to store our photos. We don't have that value yet, so we'll just leave this placeholder there. Then we have the default region. We're operating out of Oregon. And then we have our Dynamo mode on, and this means that we want our application to use DynamoDB. And then we're running this application and hosting it on port 80. Now we can select launch instance, and this will begin to go build out the different things that we need, like our security group, and we can see that our instance has launched. Now, if I select this instance ID, that brings us to a page where we can then select our instance and view some information about it. We can see things like our public IP address, our private IP address, and our public DNS name, but we can't access this directly yet. We can see that our instance state is running, but if I refresh this, You can see that we have some status checks that are still initializing. I want to wait until both of these status checks have passed. So we'll give this a few minutes and then we'll come back once it's ready. Okay, we're back and we can see that our instance state is running and the status checks have passed. Now, if I select this instance again, we can then open up our IP address in a new tab. All right, and we can see that our employee directory application has been opened in a new tab and we have an empty employee directory. This is exactly what we would expect at this point, as we don't have a place to store our photos or the employee information with our S3 bucket or DynamoDB table. We're going to look at how to build out a custom network for this, the S3 bucket, and the DynamoDB table, and make all of this highly available in an upcoming lesson. So stay tuned. EC2 is great for all sorts of different use cases, from running basic web servers to running high performance computing clusters. That being said, though EC2 is incredibly flexible, reliable, and scalable, depending on your use case, you might be looking at alternatives for your compute capacity. For example, let's say you are looking for a way to run containers at scale on AWS. Containers can provide you with efficiency and portability. In this context, I'm specifically referring to containers like Docker containers or containers that use the containered runtime. If you aren't sure what containers are, please review the readings on containers. Containers are portable because everything an application needs to run, including the application code, dependencies, and configuration, are all packaged up together as one executable, which is the container itself. Since everything is self contained, it means that you can expect your containers to behave the same way across different environments like development, QA, and production. AWS offers container services like Amazon Elastic Container Service, otherwise known as ECS, or Amazon Elastic Kubernetes Service, otherwise known as EKS. Both of these services are container orchestration tools. When you use containers on AWS, both of us offers container services like Amazon Elastic Container Service, otherwise known as ECS, or Amazon Elastic Kubernetes Service, otherwise known as EKS. Both of these services are container orchestration tools. When you use containers on AWS, you need processes to start, stop, restart, and monitor containers running across not just one EC2 instance, but a number of them together called a cluster. The process of doing these tasks is called container orchestration, and turns out it's really hard to do on your own. If you have a few containers, it's not so bad, but once you get to hundreds or thousands of containers you are managing, it can be quite complex. Orchestration tools were created to help you run and manage containers. ECS is designed to help you run your containerized applications at scale without the hassle of managing your own container orchestration software. EKS does essentially the same thing but uses different tooling with different features. We aren't going to go too much into this now, However, I did include a link to more learning resources around containerized applications on AWS in the readings following this video. The way you can interact with these container services is you manage the containers running on a cluster through the Orchestration Tools API, and then the orchestration tool carries out the management tasks. You can automate scaling of your cluster hosting your containers, as well as automate scaling of the containers themselves. Containers have a shorter boot up time when compared to virtual machines. So, if you need super fast response to increasing demand, then containers might be the service for you. Personally, I think the portability aspect that containers give are my favorite benefit of containerized applications. So, you can choose to host containers on top of a cluster of EC2 instances as your hosting options, either for ECS or EKS. However, what if you were looking for an alternative to hosting your containers? Because you either don't need access to the underlying OS or you don't want to manage those EC2 instances. Well, you can use a compute platform called AWS Fargate, which handles most of the underlying details for you. Fargate is a serverless compute platform for ECS and EKS, and we'll talk more about what serverless is coming up next. EKS does essentially the same thing, but uses different tooling with different features. We aren't going to go too much into this now. When using Amazon EC2 or container services running on top of EC2 as a compute platform, you are required to set up and manage your fleet of instances. This means that you are responsible for patching your instances when new software packages or security updates come out, setting up the scaling of those instances, as well as ensuring that you've architected your solutions to be hosted in a highly available manner, which means deploying instances across two AZs at a minimum, as we discussed earlier. This is less management and operational overhead than you would have if you hosted the same solutions on premises. But management processes will still need to be in place, and it's your responsibility to create those processes to fit your use case. This is actually really great, and in many use cases, is exactly what you want because it gives you a great deal of control over your solutions. Whatever happens on your instances and with your instances is in your hands. You can create simple or complicated setups that run and scale on AWS exactly to your specification. That being said, not every single solution requires this level of control over the underlying environment. Oftentimes, you might be looking to focus on your own business solutions and let someone else take care of the undifferentiated heavy lifting for you. Or perhaps you just simply don't want to fiddle around with scaling controls and fault tolerant designs, but you still want all of the benefits of doing so. This is where the term serverless comes in. A lot of AWS services are serverless in nature. Serverless means that you cannot see or access the underlying infrastructure or instances that are hosting your solution. Instead, all of the management of the underlying environment from a provisioning, scaling, fault tolerance, and maintenance perspective are taken care of for you. All you need to do is focus on your application. The rest is taken care of, or more accurately, the rest is abstracted from you. This means that serverless offerings are very convenient to use. You get to focus on the value that the service delivers and not the underlying implementation details, thus reducing the number of operational support processes that you need to have in place. Remember the shared responsibility model that we covered in a previous lesson? This idea of serverless impacts that as well. For example, with Amazon EC2 instances, you are required to patch the OS when new security updates are released. With serverless offerings, the line between what you are responsible for versus what AWS is responsible for moves up. You do not have access to the underlying operating system that is running the service. Therefore, you cannot be responsible for carrying out tasks like patching. You are, however, still responsible for things like data encryption and access management. Let's wrap this up. I like to think of AWS services as existing on a spectrum. On one side of the spectrum, you have convenience, and on the other side, you have control. Many services exist to give you control, like Amazon EC2, whereas other services exist to give you convenience, like the serverless compute AWS Lambda. We'll dive deeper into some of these serverless compute technologies coming up. When using Amazon EC2 or container services running on top of EC2 as a compute platform, you are required to set up and manage your fleet of instances. This means that you are responsible for patching your instances when new software packages or security updates come out, setting up the scaling of those instances, as well as ensuring that you've architected your solutions to be hosted in a highly available manner, which means deploying instances across two AZs at a minimum, as we discussed earlier. This is less management and operational overhead than you would have if you hosted the same solutions on premises. But management processes will still need to be in place, and it's your responsibility to create those processes to fit your use case. This is actually really great, and in many use cases, is exactly what you want because it gives you a great deal of control over your solutions. Whatever happens on your instances and with your instances is in your hands. You can create simple or complicated setups that run and scale on AWS exactly to your specification. That being said, not every single solution requires this level of control over the underlying environment. Oftentimes, you might be looking to focus on your own business solutions and let someone else take care of the undifferentiated heavy lifting for you. Or perhaps you just simply don't want to fiddle around with scaling controls and fault tolerant designs, but you still want all of the benefits of doing so. This is where the term serverless comes in. A lot of AWS services are serverless in nature. Serverless means that you cannot see or access the underlying infrastructure or instances that are hosting your solution. Instead, all of the management of the underlying environment from a provisioning, scaling, fault tolerance, and maintenance perspective are taken care of for you. All you need to do is focus on your application. The rest is taken care of, or more accurately, the rest is abstracted from you. This means that serverless offerings are very convenient to use. You get to focus on the value that the service delivers and not the underlying implementation details, thus reducing the number of operational support processes that you need to have in place. Remember the shared responsibility model that we covered in a previous lesson? This idea of serverless impacts that as well. For example, with Amazon EC2 instances, you are required to patch the OS when new security updates are released. With serverless offerings, the line between what you are responsible for versus what AWS is responsible for moves up. You do not have access to the underlying operating system that is running the service. Therefore, you cannot be responsible for carrying out tasks like patching. You are, however, still responsible for things like data encryption and access management. Let's wrap this up. I like to think of AWS services as existing on a spectrum. On one side of the spectrum, you have convenience, and on the other side, you have control. Many services exist to give you control, like Amazon EC2, whereas other services exist to give you convenience, like the serverless compute AWS Lambda. We'll dive deeper into some of these serverless compute technologies coming up. Now that you have learned about what container services AWS offers and what serverless means, let's continue our conversation about containers. To recap, ECS or EKS is the container orchestrator. This is the tool that is managing the container's lifecycle. Then you need the compute platform. This is where the containers actually run. Previously, you learned that ECS and EKS run containers on clusters of EC2 instances. And in that case, you are using EC2 as the compute platform for your containers. And you also have tight control over those instances. Now, EC2 is certainly not serverless. So, thinking about serverless compute for containers, I want to introduce to you a service named AWS Fargate. AWS Fargate is a serverless compute platform for containers that you can use with either ECS or EKS. With AWS Fargate as the compute platform, you run your containers on a managed serverless platform. The scaling and fault tolerance is built in, and you don't need to worry about the underlying operating system or environment. Instead, you define your application content, networking, storage, and scaling requirements. There's no provisioning, patching, cluster capacity management, or infrastructure management required. To break that down a bit, the way you work with Fargate is you first build your container images and push them into a repository like Amazon Elastic Container Registry, for example, which is a place where you can store container images for them to be pulled and deployed from. So you have your container images in your repo, and then you define memory and compute resources for your task if you're using ECS, or your pod if you're using EKS. Then you run your containers. And at the end, you only pay for the amount of vCPU, memory, and storage resources consumed by your containerized applications. Fargate does support spot and compute savings plan pricing options, just like with Amazon EC2 instances. So there is some flexibility on how you plan to run containers on Fargate. So you can still get a good amount of control for your containers deployment, but without needing to worry about the provisioning, patching, and managing the underlying operating systems or instances. And no need to scale the infrastructure in and out to meet demand like you do with EC2. As far as use cases go, AWS Fargate can be used for all of the common container use cases, including microservice architecture applications, batch processing, machine learning applications, and migrating on premises applications to the cloud. All right, hopefully you now have a 10,000-foot view of AWS Fargate. You can see how Fargate is an example of how serverless simplifies your operations and management for running scaled container solutions. AWS Lambda is one of the serverless compute options you have available to you on AWS. Lambda allows you to package and upload your code to the Lambda service, creating what is called a Lambda function. Once you create a Lambda function, it isn't always running all of the time. Instead, Lambda functions run in response to triggers. You can configure a trigger for when you want your function to run. And from there, the Lambda service waits for the trigger or polls for an event to trigger the function, depending on what the trigger is that you choose. There's a long list of available triggers for AWS Lambda, and new ones are being supported all of the time. So I won't run through them all now. However, a couple of common examples of triggers for Lambda functions are an HTTP request, an upload of a file to the storage service Amazon S3, events originating from other AWS services, or even in app activity from mobile devices. When the trigger is detected, the code is automatically run in a managed environment, an environment that you do not need to worry too much about because it is automatically scalable, highly available, and all of the maintenance of the environment itself is done by AWS. You do, however, get to choose the language your Lambda function is coded in, the amount of memory and CPU your function is allocated in the environment, permissions, dependencies, and many other aspects of how the function runs. If you have 1 or 1,000 incoming triggers, AWS Lambda will scale your function to meet demand, each in its own isolated environment. Lambda is currently designed to run code that has a runtime of under 15 minutes. So, this isn't for long running processes like deep learning or batch jobs. You wouldn't host something like a WordPress site on AWS Lambda. It's more suited for quick processing like a web backend handling requests or a backend report processing service or microservice hosting. One of the best things about Lambda is that you aren't billed for code that isn't running. You only get billed for the resources that you use, rounded up to the nearest 1 millisecond interval. To understand Lambda more thoroughly, let's run through a quick demo. In this demo, I will create a Lambda function that resizes images uploaded into the employee directory to be uniform thumbnail size. It makes sense to create this sort of logic with the Lambda function. You don't need an application to be running 24/7 on EC2 to resize photos uploaded to the application. You really only need to run the resize logic when a new photo is uploaded. So here's our diagram for the app. What I want to do here is when a new photo is uploaded to S3, it triggers a Lambda function that then resizes the image and uploads it into that same S3 bucket, but to a different location than where the original image is stored. All right, let's go ahead and build this out. You can see that I'm already in the AWS Lambda console, and I'm going to first click Create Function. Next, we get to select what type of function we want to build. Do we want to author a function from scratch? Do we want to use a blueprint, which will give you some sample code and configuration presets? Or you can use a container image with AWS Lambda, as Lambda does support running containers. We're going to author a function from scratch. For the function name, we will call this resize image, and then we get to select the runtime. The runtime is the language that your Lambda function is written in. Because with Lambda, it runs in the Lambda environment, but it's still your code. So I'm going to go ahead and select Python 3.9 for this, as we wrote this function in Python. And then we have to select the permissions. And the permissions are going to be delegated to the function through IAM roles. So I'm going to click use an existing role. And then if I expand this drop down, we can select Lambda S3 full access, which is an IAM role that I've already created in this account that will give this function permissions to read and write from S3. Now we can scroll down and select create function. Now we can add a trigger for this Lambda function, and I'll select add trigger. And here we get to configure the trigger source. And if we expand this dropdown, you can see a list of AWS services that can act as triggers, like API Gateway, an application load balancer, DynamoDB. We're going to scroll down and select S3 for our trigger. And then we need to select which S3 bucket will be the event source. I already have an S3 bucket created in this account called Photo Upload Bucket MW. We'll select that one. And then if we scroll down, I'm going to select the event type. I want to select only a put. So I want put operations to trigger this AWS Lambda function. Then we can provide a prefix. With this prefix, what we're essentially doing is we're going to say, I only want to trigger this Lambda function if a put occurs in a specific location inside of this bucket. We're going to upload photos to an input prefix, and that will then trigger the Lambda function. We then need to acknowledge that if we're using the same S3 bucket for both input and output, that it could cause recursive invocations. So the way that we're getting around that is by supplying this input prefix. The event will be triggered when an image is uploaded to this prefix, but then the output will actually be uploaded to a different location. We'll have an output prefix where the image will be uploaded to. So we're going to go ahead and acknowledge by checking this checkbox and then click add. Now back on our function overview page, what we need to do next is actually upload the code for this. So if we scroll down, we can select the code tab. And then you can see that there's a stubbed out Lambda function here that essentially just says, hello world, hello from Lambda. And what we need to do is upload our code. So I'm going to click upload from and then select zip file, click upload, and then I will select this resize image.zip, click open, and then click save. All right, our function has been successfully created. We have our trigger defined and we have our code uploaded. What I want to do now is test this out by actually uploading an image to S3 and then viewing the output. So in the search bar, I'll type in S3 and then select S3. Then from here, we'll select the bucket and then we'll go into the input folder and then select upload. Click add files, and then I'll upload Seth's image and select open and then upload. We can see that that upload was successful. So now if we go check, we should see the output with the thumbnail version of that image. So now going back into our bucket, if we go up one level, we can now see that the output prefix has been created. So I'll select that. And we can see that the thumbnail image was created. And that's it. That's how you create an AWS Lambda function. You could host the entire employee directory applications backend on Lambda with some refactoring, but I'm going to go ahead and save that for a later conversation.